Hello and welcome back to Lecture 3, 4.5, Diodes and Rectifiers. Now we're going to get into how to use these actual devices in circuit. So diodes are the device and rectifiers are kind of an application of diodes. It's a circuit you might want to build using a diode. So diodes we've been talking about a lot, looking at the semiconductor background of these things, but now let's actually look at how we'd want to deal with them and think about them when they're in a circuit. So a diode used as a rectifier means that since it only allows current to go in one direction, basically, it can turn this AC signal into more of a DC signal. We would just see current, the positive part of the voltage here. So basically how the diode works is if the voltage is less than the on voltage, some kind of minimum voltage to get an appreciable current for the diode, then we'd see no voltage over here because it's not going to conduct through there. This is infinite resistance, so it's like a voltage divider with infinite resistance. If the voltage is bigger than that, though, then this conducts pretty well. We've got this drop of V on, usually about 0.6 volts for a silicon diode. That depends on the material that the diode is made of. Then with that 0.6 volts, most of the voltage appears across the output resistor there. Now you know that really the diode is modeled by this current equation that we had earlier, but look at this exponential curve. I mean, this is basically an approximation of a right-angled, just like a right angle here, right? So it goes essentially 0, and then after the turn-on voltage, say about 0.6, it's infinite current if you try and increase above that, like to the amount of current that you'd need. Try and figure this out on your own. See how much current you would get out of a diode if you had 1 volt up there, and you'll find that, wow, that's kind of a ridiculous amount of current. In fact, the exponential is kind of obnoxious, and we'll look at some solutions for solving for diodes in equations later. An accurate model of a diode also includes a small capacitance if we want to be technical about it, because you've got this little region here that doesn't conduct surrounded by these materials that do. So it's basically like there's a little bit of a capacitor there. When you get a diode, we draw it in a circuit like this, but most of the time it'll really look like this if you're going to look at one in the lab. So which side is the direction that it conducts to? It conducts that way. From left to right, the stripe indicates where the cathode is, which is the area the current comes out of in forward bias. Right. So how do you deal with a diode like this? Suppose we want to just say, all right, well, let's try and get a decent solution. We don't need to use the full diode equation. I just want to look at this and get some kind of intuitive sense about how much current I'm going to get. We know that in forward bias, we're going to get some, it's not going to resist very much, but how do we solve this circuit? Basically what you do is you first assume that the diode is not going to let any current through. So assume it's got infinite resistance, and then find out what voltage would be placed across it. If that voltage is more than the turn-on voltage, about 0.6 volts for silicon, then you can say, okay, the diode's just going to drop 0.6 volts, and it'll take whatever current is trying to go through it at that 0.6 volts. So let's look at this one. We've got 10 volts here and 1 kilo ohm there. We're going to try and solve for the current. So give that a shot. Welcome back. How'd you do? If the diode has infinite resistance, then the current's 0, the voltage across it is 10 volts. 10 is bigger than 0.6. Let me just check that on the calculator. Yes, 10 is larger than 0.6 volts. So therefore, we've got the diode in forward bias. It's turned on. Current is going through this diode. So the voltage that appears across the resistor is just 10 volts minus this 0.6 volt drop that's necessary there, so 9.4 volts, so the current is 9.4 milliamps. All diodes have a maximum current that they can actually handle. You can look on the data sheet to find out what this current is, and you should make sure that you don't go past this without damaging the diode. So you always need a resistor in series with your diodes next to a power supply. You can't just put the power supply right across the diode, or it'll put way too much current through the diode for most power supplies. Even if you want to try and measure the resistance of a diode, you say you've got this diode, you put your multimeter attached to it. The multimeter is going to try and drive some current through the diode and measure the voltage that's necessary to drive that current. So this current that it's driving could be too much for the diode and could really damage it. So that's why you should put your multimeter into diode checker mode. Then it's going to try and push a fixed current through and measure whatever small voltage is necessary to do that. Rectifier is an application of diodes. This is a circuit that is used to rectify an input voltage, to stop it from being negative. So we haven't really talked about AC yet, but you remember some simple AC stuff from first year and second year circuit. So here's our AC supply. It would create a sine wave input there, but the diode stops the voltage from being placed across this resistor if the voltage is negative, or if it's not larger than this 0.6 volt drop. So the output is this thick black line here. That's what we see at V out there. We get the voltage placed across there, which is, so the input voltage kind of passes through if it's positive, but it doesn't pass through if it's negative. And so we've rectified the circuit by getting rid of the low voltage parts, the negative voltage parts. This is not exactly DC yet, but if we then take this and pass it through a low pass filter, something that we'll learn about in chapter 2, then we can sort of smooth this out a little bit. You can imagine taking the average. This gives us a DC signal, but it's kind of low. The input was about 4.5, I guess 5 volts, but the output is looking like it's more like 2 if we take the average of this. So we lost a lot of power there. We can get a better rectifier by doing this kind of design. This is a full wave rectifier. Now the average is going to be a little bit higher than previously. So this is going to be a bit better than the past one. I guess this one is not actually 2. It's more like, so 2 is sort of the average of this one pulse. Maybe the whole thing's average is more like a 1, but this one's going to be a bit higher. Now the disadvantage of the full wave is because every path through, you've got to pass through 2 diodes, so you drop double the diode voltage. And so you wouldn't actually want to use a full wave rectifier if your input voltage signal is too low, but for an appreciable input voltage signal, this is a pretty good way to do it. How does this work? Look at this circuit here. There's no connection at this spot. Because there's no little dot there, no black dot at this connection. This just means the wires are passing over each other. These wires are connected though. This is connected, that's connected, that's connected. So if this is a positive voltage, then what happens? Current tries to go this way. Can it go that way? Nope, gets stopped by the diode, goes up through there, drops across one diode. Then can it go there? Nope, so it appears there. So the positive voltage appears there. The negative side of it tries to go up this way. And then the negative voltage, can it go this way? No, because it's a negative. So it's trying to draw current. So it can actually go backwards through a diode and appears there. So when you've got a positive voltage at the top of this voltage supply relative to the bottom, then current can go up out of it through this path and can come in from this path on the bottom. If the opposite's true, if we want to have current going out the bottom on the other side of the cycle, then it would go up this way and through this diode. And where does it come from? It goes through here. To get back to the voltage supply, it's got to go through this diode this time and back in the top. Dynamic resistance. One way to incorporate diodes into your circuits is to try and figure out what their dynamic resistance is. I'll just take a second to define something else first. A linear system's a system that has the linearity property. Linearity property means two things, really. It's if you were to take the system of the sum of inputs, then it gives you the sum of the outputs that you would have gotten originally for those inputs. And also you can take out scalar multiples. So if you were to double the input, then you would double the output. This means that if f is a linear operator, then f at a x1 plus b x2, you can split it over the sum, and you can take out the constants, and then you just have that it's a times f at x1 plus b times f at x2. This is really a useful property of systems. Operators that have this in math are multiplication, differentiation, integration. You like to use linearity properties when you can. Linear circuit elements like resistors similarly have this property that the output is a constant multiple of their input. This is pretty useful to use, so it lets you do things like superposition theorem. Power scales like the square of voltage or current, so linearity of voltage or current requires nonlinearity of power. You have to be careful if you're going to try and use superposition to solve for what power is output in an element. You can't find the power from one supply and then just add it to the power from another supply acting individually. What you have to do is add the voltages or the currents from each of those supplies acting individually, and then get the total voltage and calculate the power from that. However, a diode is a nonlinear circuit element, so its resistance is not a constant as current or voltage changes. This means you have to be careful if you're going to try and use superposition with nonlinear circuit elements. It's not going to work the same. What we can do is define a dynamic resistance for a diode if we want to work with AC signals. Basically, the dynamic resistance is defined as the derivative of the voltage to the current through the diode, voltage across the diode to the current through the diode. From our current equation, solve for voltage, we can take a derivative, remembering to use the chain rule to help get rid of the IS that would have appeared on the top there. And then effectively, since the IS is usually really small, the saturation current's small compared to the diode current, the diode resistance is basically kBT over E divided by I, which means the diode resistance decreases with increasing current that's going through it. The dynamic resistance approaches zero. Okay, now let's look at a way to solve for the diode current, for the current in a diode circuit. So we're going to do this circuit right here. This one, we've got an input voltage, we've got an output voltage, and we've got a resistor and a diode. So the voltage is going to cause a current to go through the resistor according to Ohm's law. I is the difference in voltage over the resistance, VI minus VO over R. And the diode, we know that it has a current given by IS, e to the q V naught over kBT minus 1, that's using the ideal diode equation. If we combine these two, then, okay, now all we got to do is solve for V naught. All right, go ahead. Take a minute to do that. Welcome back. How did it go? Right. Probably not the easiest equation to solve after you give it a shot. The problem is the exponential. You can't really get the V naught out of there without messing up what's going on the other side. So if you try and get rid of it, you end up getting a ln of V naught over here at least. So you can't really solve this analytically, but you can do it graphically. I mean, this is just one function, I versus V and versus V naught, and this is another I versus V naught function. You can plot both of those, and then wherever the I and V are equal from this equation and this equation, you've got it solved, right? Because then the I's are equal and the V naughts are equal. So let's just do that. This is the diode one, and this is the straight line one from the Ohm's law and the resistor. Okay, we've got a point right there. Let's call that the quiescent point. And then we've got the current versus voltage solved for. In circuit terminology, this is a common thing to do. So they call this straight line one from the diode, or from the resistor rather, the load line. It depends on the circuit that the diode finds itself in. Now, up here, back when we looked at the dynamic resistance, the dynamic resistance of the diode was increasing with current. And you may have been thinking, okay, well, why even define a resistance? Because this is going to be changing all the time with current, so we can't treat the diode like a resistor. Well, if you have a DC voltage applied with a small like AC ripple on top of it, so the voltage maybe goes between 4.0 and 4.1 volts in AC, so it's mostly around 4.05, then you'd put in your 4.05 volts in DC to get the spot that you're at, like you'd solve the load line for that input voltage, which would be placed up here. This is where the input one was. And after solving that, you'd get your quiescent point, and the AC is just going to create a ripple up and down on that, like a left and right in voltage, up and down in current. Let's look at this iterative solution. So if we rearrange this for the VO from the exponent, then we get this kind of equation, which is in terms of the voltage. We've got voltage on the left side and the voltage on the right side. We can't explicitly solve for the VO, and that's why this is that's why this is kind of a problem, and we've got to do things like plot out the function and plot out one function, plot out the other function, note where they're equal, as we do in the load line. But another thing you can do is just guess a value for VO and substitute it into the right-hand side of this, and then use that to get your new guess. Because ln is a really smooth function, this works quite well actually. If we just guess 0.7 and then substitute it in, we get 0.264941. Substituting that in, 0.287972. Substitute that in, and we get 287972, 287154, and proceed like this. This is just a script I wrote with Excel that does this. It just repeatedly subs it in. And this smooths out really quickly because ln is a very insensitive function of x unless x is extremely small. If we, you know that this doesn't work if you leave it as an exponent. If you substitute a v into the right-hand side, this blows up pretty quickly. So it's really necessary to solve for the ln version of this if you're going to try the iterative solution. This is a nice thing to do with your max standard calculator. So just solve, write in an equation where VO is the answer. So just type in your first guess, 0.7, and then VO will be the answer of that. Then what you do is you write your new expression for this using, instead of typing out what your guess is here, put in amps. Then you hit enter, and the new answer will be your next guess, but you've still got this expression here with ants right there. So you can hit enter again to do the iteration a bunch of times. So you type out your expression once, hit enter 5 or 6 times until it stops changing, and there you've got your iterative solution for the voltage. Let's go back to this calculation we did earlier. This is one we did where we just said it was a 0.6 voltage drop, and we found that it was 9.4 milliamps. How different is it with iteration? This time try using IS is 3 nanoamps and kBT over E is 25.7 millivolts. Give that a shot. All right, here we go. Substituting into the diode equation after we've solved it for the logarithmic form by solving for voltage first. And then since we're actually looking for current, what I'm going to do is substitute this voltage into this equation to eliminate the voltage. Now we pick our starting guess as our current from last time. May as well. The new guess turns out to be very close to that and not changing very much. So instead of 9.4 milliamps, it turns out it was actually 9.6 milliamps. So this diode in this particular setup, the current was low enough that it only ended up dropping about 0.4 volts instead of the 0.6 that we guessed. The last thing that we're going to talk about in diodes is the idea of Zener diodes in reverse bias breakdown. Diodes conduct very well if you put them in forward bias, but in reverse bias, they block the current. Up to a point. If you put in too much reverse bias, then the diode will do what's called breaking down. It'll start to conduct a lot of current. There's 2 physical mechanisms for this that may be responsible. The first is called Zener tunneling. Let's look at the band structure here. If you reverse bias the diode, you start to raise the P side up in potential energy, lower the N side. So the conduction electrons over here have a really hard time to jump up to the conduction band over there, and that's why the diode doesn't conduct very well in the normal way. The valence band electrons, though, if it's really reverse biased, here, look at the valence band on the right-hand side is actually above the conduction band on the left. So that means that there's this tunneling barrier which is getting kind of thinner as we reverse bias it more, where the electrons from here can jump over. This was the generation current that we talked about earlier. It's not normally a big effect until you get into reverse bias. For this tunneling mode to take place, the depletion width has to be reasonably small. It's kind of a combination of the depletion width and the amount of reverse bias. The depletion width is dependent on the doping levels. If you have really heavy doping, then you're going to have a thin depletion region, and that means that there's going to be more, it's going to be easier for tunneling to take place across this barrier in reverse bias. There's a completely different mechanism for breakdown called avalanche breakdown. Avalanche breakdown happens due to the minority carrier. So rather than the the electrons from the valence band over here actually jumping into the conduction band. The minority carriers, let's just look at the p side, for example. Minority carriers are these electrons that are up here. There's not very many of them because of the p doping, so there's a lot of holes that eliminate those the electrons that are there. The electrons that are there are just from thermal excitation. Now, those electrons always are seeing especially in reverse bias, there's a potential for them to drift over to the left. When they get to this, they don't see a barrier. They just fall down over to the other side. That's responsible for the reverse bias saturation current. Normally, that's not a very large amount. The reverse bias saturation current, say in a silicon diode, typically around order of nanoamps, very small contribution to current. But if you reverse bias the diode enough that when these things are jumping across while they're on their way across, the depletion width especially, they gain so much speed, the electrons can get going so quickly because of that applied potential, that when they do collide with the lattice, they don't just lose their speed, they knock out additional electrons, causing an avalanche of electrons because those new ones also gain enough speed to knock out additional ones. So then a lot of conduction can happen, and that's called an avalanche breakdown. Just like if and I don't know if you've ever thought about how an avalanche works in snow, but the snow falling gains enough kinetic energy from gravitational potential energy that when it hits snow that's stationary, it can knock that out, which then in turn makes more and more snow, leading to an avalanche. A Zener diode is a special diode that's designed to be operated in reverse bias breakdown. Despite calling this Zener tunneling, Zener diodes can actually be designed to operate on avalanche breakdown. It's not really important for our purposes to understand exactly how a given Zener diode is designed to work. A Zener diode, the idea is it's got a very sharp breakdown in reverse bias, and because of that, because this can be even sharper of a cutoff than in the forward bias, they're designed to be operated in reverse bias. In forward bias, they just behave like a regular diode, but in reverse bias, they've got a specific breakdown voltage where they start to suddenly conduct a whole lot of current. So it's kind of like they're a diode in two directions, but the direction they start conducting is sharper in the reverse, and the voltage that they start conducting at is a sharper cutoff in the reverse bias and a different voltage than in forward bias. Because of this, Zeners are often used if you wanted to make a voltage regulator. Say like this sort of circuit, you've got an input voltage, then rather than the voltage divider that we looked at from chapter 1, this would maintain a pretty strong specific voltage here. Why does that work? Well, if VI is greater than the reverse bias, if it's less than the reverse bias breakdown, then we just get VI transported across. It's like this is an infinite resistance here. But if VI is greater than the reverse bias breakdown, let's suppose VI is a little bit unstable. Suppose this is 7 volts and the reverse bias breakdown is 4. Then we'll get 3 dropped across here, at least 4 volts here, so it'll put out any current. Now what happens if this raises up from 7 to 8? Then the voltage here can't rise because that would mean an infinitely large current going through here, and as soon as that current tries to go up, it'll raise the voltage across the resistor. So instead, all of that just appears across the resistor. If this voltage jumps up or jumps down, those voltage changes just happen across this resistor in the divider, and the Zener keeps that constant voltage across it, meaning that it's quite a good regulator. All right, we're skipping sections 454 and 455 onto exercise 410. Write explicitly the function for the output for each of the two circuits shown in figure 422A and 423A, which are the half wave and full wave rectifiers we looked at earlier, for an input of 5 volts sine omega t and load resistance of 50 ohms, assuming the simplified diode voltage drop in forward bias of a fixed 0.6 volts. Give that a shot for the half wave rectifier first. All right, so the simplified diode voltage drop in forward bias means that if the input is a positive voltage here, then if it's above 0.6 volts, the diode voltage drop is exactly 0.6 volts. And whatever extra voltage would go into making current through this resistor, but would also tell us the output voltage directly. We don't really need to know the load resistance if we're going to be using the simplified diode equation. We may need to know this and this size if we want to find out afterwards whether the simplified diode equation was justified, but as long as we're going to be using it for sure, then this is a red herring. We're not going to be using this at all in this question. So if the voltage is less than 0.6 volts, then whatever voltage is on the supply goes directly across the diode, and none of that gets across the load because there's no current. So with no current, the voltage across a resistor is 0. All right, how do we write an equation for that? The idea that the output voltage will be whatever the input one was minus 0.6 if the input is at least 0.6. Well, that's with the max function. The output is the input minus 0.6 volts. You can use the same idea to solve the full wave rectifier. I'll give you a chance to do that. Okay, so the full wave rectifier, same idea. We end up having two max functions. Now, though, we're subtracting 1.2 volts. The reason is because no matter which path we take in the full wave rectifier, whether we go through the top here and up that way, meaning that we came from this path this way. So one way down through the resistor is that way, and another one down through the resistor is that way. So no matter which path we ended up, we actually took, we go through two diodes. Note that there's no path up through the resistor, by the way. It's kind of why the full wave rectifier is a full wave rectifier. It's a rectifier. It doesn't allow current to go the other direction. It just hits two diodes going in that direction. Going down through the resistor, though, there's one of two options, which go through the voltage supply in opposite directions, depending on what sign it was. Okay, so we have 5 volts sine omega t minus 1.2 volt. Pretty standard stuff in the forward direction. It's just subtract off twice the voltage drop on the diode. But in the reverse direction, it's minus 5 volts sine omega t, then minus 1.2 volts. The reason for that is that minus 5 volts sine omega t is going to be itself positive when the voltage supply is on its negative swing. And that's what we want, this positive number, again, minus 1.2 volts, max of that thing, and 0. Only one of these max functions is ever going to be active at the same time, so there's no way that adding the two maxes is going to give us something that's bigger than either one individually. Exercise 4.11. Sketch the output for the circuit shown in this figure as a function of time in the limit that V on is negligible, so no voltage drop across the diode in forward bias, and in reverse bias it still does the diode thing of not letting anything go through. Take the case when the voltage supply labeled with V is a DC voltage that is half the max value of this AC voltage input. Give that a shot. All right, so this Let's look at some cases here. If this voltage is higher than this voltage, so for the part of this cycle when it's on like the top, the maximum voltage that this is outputting, then we've got a high voltage here, and as long as the output isn't connected to anything that's draining this current a lot, that's drawing a lot of current through this and dropping that voltage across the resistor, that voltage still exists right over here. So no current can go through this, and the voltage. So that means the voltage that's here is also on this side of the resistor, and so we've just got this voltage repeated on the output. The extra voltage from the AC supply versus the DC supply, like it goes up to twice this voltage, would just appear across that diode. It's a reversed bias diode in that case. Now, when this drops lower than this voltage, then what happens is the output voltage here would have been lower than this voltage, but now the diode will start conducting in that case. So all the current that needs to will just go up through this diode and then across the resistor. Looking at the plot of this, we've got the AC voltage for a quarter of its cycle, not quite a quarter of its cycle, till it gets to half of its height, a little bit more than a quarter of its cycle, then dropping down and back up. During the parts that the AC voltage would be less than 0.5 of its max, the DC voltage clamps it from dropping any lower. Exercise 413. Determine the quiescent point, i.e. find the current and voltage and dynamic resistance at that quiescent point for the current shown in figure 4.25 with R is 10, V is 1 volt, V in is 1, diode saturation current 1 microamp at room temperature. All right. So the first thing you have to do is find the quiescent point. You can do that graphically or iteratively. And the next part is to find the dynamic resistance at that quiescent point. Remember, you take for the diode part only, not the resistor part really, the diode part, you find the rate of change of the output relative to the of the voltage relative to the current. That's what gives you the resistance of the diode. Dynamic resistance just refers to the diode's resistance. All right, so by combining the current through the resistor, saying that that's the same as the current in the diode, we've got this equation, and then you can do you can substitute in your numbers here: E over kBT, 38.6 per volt. Then, putting in the given values, we can plot two functions. The left-hand side is your load line, and the right-hand side your diode. This is the iterative solution. Plotting them and finding out where they're equal, you can find the voltage and then the current. You also could do the iterative, I think I called this the iterative. This is the graphical solution. You also could have done the iterative solution, which is to solve this for V out on this side so that you get a logarithmic function, and then proceed to solve, guess something, sub it into the log, find out what V you get, and then repeat until it stabilizes. Either way, you'll come up with a voltage around 0.29 volts and this current. Now for the dynamic resistance, it's the rate of change of voltage with respect to the current for the diode one before we've gone and rearranged it and all that, and we get 0.35 ohms. What this means is that if we were to go and change the input voltage, the difference in current that we would get from that would behave as if the diode was a resistor with only 0.25 ohm resistance. Since that's very low, it explains why a lot of the time we'll just say that diodes are very good conductors in forward bias and almost look at them like we like to as one-way valves for current.